Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Welcome to this presentation on VLSI chip, Physical Design Fundamentals Part 1. In this session, we will explore how a VLSI chip structure of devices and interconnects impacts the power and performance characteristics. Also, the review technology scaling that introduces parasitic effects influence the chip operation. So, let's get started. The figure shows the top view of the fabricated silicon chip. At the top level, the chip is organized into the core area, which houses the logic. The big functional blocks like memory, analog etc. known as macros are placed at the chip edges. The chip periphery is surrounded by the I/O pad area that enables external communication. The power distribution network spreads supply rails across the die, ensuring voltage stability, while the clock network synchronizes operations but adds significant load and switching activity. Parasitics from wires, vias, and devices begin to influence the design, degrading power integrity, slowing performance, raising thermal stress, and reducing reliability. As parasitics increase with scaling, they amplify IR drop, crosstalk, and heat, ultimately constraining efficiency and limiting the lifetime of the chip. In the top view, the chip reveals its structural balance, with the dense logic core surrounded by I/O pads that act as gateways for external communication. The macros are high-power dissipating element and are placed at the chip periphery and avoid hotspot creation. The power distribution network appears as a lattice of rails and straps, designed to deliver current uniformly across the die. Overlaid on this, the clock network forms a synchronized backbone, ensuring timing consistency across millions of switching elements. The cross-section view exhibits the base layers on the substrate that house the active devices, and above them stacked metal interconnect layers carry signals and power. These layers are capped by a passivation layer that protects the chip surface from environmental and mechanical stress. Together, the base layers, interconnects, passivation, and I/O pads define the chip's structure and functionality, while parasitic effects from interconnects and devices influence power, performance, thermal behavior, and reliability. The semiconductor processing layers shown in the panel illustrate how multiple patterned films are stacked to build the device. At the base lies the silicon substrate, with doped regions and deep trench isolation defining the foundation. Above it, the gate oxide and polysilicon form the control element of the transistor. Diffusion layers create the source and drain terminals, enabling current flow through the channel. Successive oxide, via, and metal layers overlap to provide connectivity and routing across the chip. The MOSFET structure emerges as a composite of these differently patterned, overlapping layers, each contributing to electrical functionality. Together, they transform raw silicon into a field effect transistor capable of switching and amplifying signals in integrated circuits. Depending on the technology node, multiple interconnect layers named M1 through MXX are stacked, each with different dimensions to serve logic cells, power straps, clock network and power rings. The power distribution network delivers power across the die, and the clock distribution network carries the external clock signal into the chip. The clock tree propagates the clock signal to the pins of logic gates, ensuring coordinated switching. The overlapping metal layers are isolated by dielectrics yet vertically integrated to optimize routing density and area. This isolation, however, introduces parasitics that limit speed and dissipate power. To minimize these effects, adjacent layers are routed in orthogonal directions, reducing coupling and cross-talk. Vias connect the different vertical layers, while metal pins of cells and pads enable net connectivity. Ultimately, interconnect parasitics directly impact the power efficiency and performance of the die, making their optimization critical in chip design. The primary objective of VLSI chip design is to achieve the optimum balance between performance, power consumption, silicon area, cost, and long-term reliability. These objectives are influenced by the chip architecture, fabrication technology, device dimensions, interconnect characteristics, and operating conditions. As technology continues to scale, increasing transistor density and shrinking geometries introduce significant electrical and physical challenges. Parasitic resistance, capacitance, and inductance, together with thermal effects and process variations, increasingly limit the achievable performance. Consequently, modern VLSI design requires careful optimization to satisfy stringent timing, power, area, and reliability constraints while ensuring robust and efficient chip operation. The table illustrates how technology scaling progressively changes the dominant parasitic effects and their impact on VLSI chip performance. Technology nodes represent successive generations of semiconductor manufacturing, where transistor dimensions and interconnect geometries continue to shrink to improve integration density and performance. While scaling enables billions of transistors to be integrated on a single chip, it also significantly alters the electrical characteristics of the interconnects. Narrower and longer metal lines increase parasitic resistance, closely spaced conductors increase parasitic capacitance, and faster switching currents make parasitic inductance increasingly important. These unavoidable parasitic RLC elements introduce propagation delay, higher dynamic power dissipation, voltage drop, cross-talk noise, and signal integrity challenges. Consequently, in advanced nanometer technologies, interconnect parasitics have become one of the dominant factors limiting the speed, power efficiency, and overall performance of modern VLSI chips. The following are the major challenges encountered in modern VLSI chip design. Technology scaling has enabled a dramatic increase in transistor density, allowing billions of devices to be integrated onto a single chip. This higher integration has significantly improved computational capability and functionality, but it has also increased power density and design complexity. Growing performance demands require higher operating frequencies and faster switching speeds, leading to increased power consumption. In portable and battery-powered systems, reducing power consumption is essential to maximize battery life and energy efficiency. The resulting power dissipation generates heat, creating thermal constraints that can limit performance and increase cooling requirements. Elevated temperatures and high current densities accelerate reliability degradation through mechanisms such as electromigration, bias temperature instability, and hot carrier injection. Consequently, balancing performance, power, thermal management, and long-term reliability has become a fundamental challenge in modern VLSI chip design. Every interconnect, due to the material property, creates parasitic resistance. This intrinsic or parasitic resistance is determined by the conductor material's resistivity and the physical dimensions of the interconnect, including its length, width, and thickness. As technology scales, narrower and longer metal lines significantly increase the resistance of the interconnect network. When switching currents flow through these resistive paths, electrical energy is dissipated as heat according to the Joule heating principle, represented by I²R power loss. The resulting self-heating increases the local interconnect temperature, which, due to positive temperature coefficient, further increases the net resistance and degrades signal propagation. Consequently, interconnect resistance has become a major factor limiting the power efficiency, speed, and long-term reliability of chips. To maximize routing density and minimize chip area, modern designs employ multiple stacked metal layers for signal and power routing. Closely spaced interconnects within the same metal layer create lateral or intralayer coupling capacitance, while overlapping conductors on adjacent metal layers generate interlayer capacitance. In addition, the vertical sidewalls of neighboring metal lines form sidewall capacitances, which become increasingly significant as technology scales. These parasitic capacitances increase the effective load seen by the driving circuits, resulting in slower signal propagation, higher dynamic power consumption, cross-talk noise, and increased switching delay. Excessive coupling can also introduce signal glitches and timing uncertainty, degrading overall circuit performance. To minimize these effects, adjacent metal layers are commonly routed in orthogonal directions, reducing capacitive coupling and improving signal integrity in high-density designs. Although parasitic inductance was once considered negligible, it has become a significant concern in modern high-speed chips due to extremely fast switching currents. Rapid changes in current generate d by dt, voltage fluctuations, producing supply voltage noise and reducing the stability of the power delivery network. These transient voltages also cause ground bounce, shifting the reference ground potential and increasing the possibility of logic errors. Inductive energy stored in interconnects and package connections further produces signal ringing, resulting in voltage overshoot and undershoot that can stress device reliability. In clock distribution networks, parasitic inductance contributes to clock jitter and clock skew, degrading timing accuracy and synchronization across the chip. Consequently, parasitic inductance has become an important factor influencing power integrity, signal integrity, timing performance, and the reliable operation of the chip. A MOSFET is formed by the precise overlap of multiple semiconductor fabrication layers, including the silicon substrate, source, and drain diffusion regions, gate oxide, and polysilicon gate. Together, these layers create a voltage-controlled device that regulates current flow between the source and drain through an electrically induced channel beneath the gate. While these overlapping and electrically isolated layers are essential for transistor operation, they also form unavoidable intrinsic parasitic capacitances. The major capacitances include the gate-to-source capacitance, CGS, gate-to-drain capacitance, CGD, gate-to-body capacitance, CGB, and the source body, CSB, and drain body, CDB, junction capacitances. Among these, CGS largely determines the input charging requirement, while CGD, commonly known as the Miller capacitance, has the greatest influence on switching speed by coupling the input and output during transitions. The combined effect of these parasitic capacitances increases the charging and discharging time of the transistor, resulting in higher dynamic power consumption, increased propagation delay, slower switching speed, and limitations on the maximum operating frequency of the designs. The figure shows the physical layout of a typical CMOS inverter, constructed by combining multiple fabrication layers such as diffusion, polysilicon, contacts, and metal interconnects. The PMOS transistor is placed in the N-well and connected to the VDD supply, while the NMOS transistor is fabricated in the P substrate and connected to VSS. The vertical polysilicon gate crossing the diffusion regions forms the conducting channels of both transistors, and the metal layers provide the input, output, and power connections. Every overlap between conductive layers, together with the insulated junctions and interconnects, creates intrinsic and layout-dependent parasitic capacitances, resistances, and junction capacitances. These parasitic elements combine to form the effective load seen by the inverter during switching. As technology scales, the influence of these parasitics becomes increasingly significant, increasing dynamic power dissipation, propagation delay, signal transition time, and limiting the maximum operating speed. Consequently, the physical layout of a CMOS gate plays a vital role in determining the overall power, timing, and performance characteristics of a chip. This equivalent CMOS inverter circuit illustrates the intrinsic parasitic capacitances that determine the switching behavior and timing performance of a logic gate. Both the PMOS and NMOS transistors contribute gate, diffusion, and junction capacitances, while the gate-to-drain capacitance, known as the Miller capacitance, provides capacitive feedback between the input and output during switching. This Miller capacitance effectively increases the input capacitance, requiring the driving stage to supply additional charge and discharge current. Consequently, The effective input capacitance is the combined contribution of the PMOS and NMOS gate capacitances, together with the Miller capacitances of both devices. At the output, the inverter drives the input capacitance of the succeeding CMOS gate, in addition to the interconnect and diffusion capacitances. The output resistance of the inverter along with the output capacitance determine the output rise and fall times, while the source driving resistance and the effective input capacitance determine the input transition time. The combined charging and discharging delays from the input pin to the output pin define the propagation delay of the CMOS gate, making parasitic capacitances the primary contributors to gate timing, switching speed, dynamic power dissipation, and ultimately the performance of the chip. Dynamic power is the dominant component of power dissipation in a CMOS inverter during normal switching operation. Every time the input changes logic state, the PMOS and NMOS transistors alternately charge and discharge the total output load capacitance. This load capacitance is the combined effect of transistor parasitic capacitances, interconnect, diffusion, and the input capacitance of the next logic gate. During a low to high output transition, electrical energy is drawn from the power supply to charge the load capacitance. During the subsequent high to low transition, the stored energy is discharged through the NMOS transistor and dissipated as heat. The dynamic power consumed by the inverter is therefore proportional to the total load capacitance, the square of the supply voltage, and the switching frequency. Consequently, increasing the clock frequency, supply voltage, switching activity, or load capacitance directly increases dynamic power consumption, making it one of the most important factors affecting speed, battery life, thermal performance, and the overall efficiency of the chips. The short-circuit power dissipation occurs during the finite transition period of the input signal, when the input voltage passes through the switching threshold of the CMOS inverter. During this interval, both the PMOS and NMOS transistors are simultaneously turned on, creating a direct conduction path between the power supply, VDD, and ground, VSS. The resulting short-circuit current flows only for the duration of the input transition, as illustrated by the current pulses in the waveform. The magnitude of this current depends on the input rise and fall times, the supply voltage, transistor sizing, and the output load capacitance. Slower input transitions increase the overlap conduction time, producing larger short-circuit currents and higher power dissipation. Although short-circuit power is generally smaller than dynamic switching power, it becomes increasingly significant in high-speed and heavily loaded CMOS circuits. Therefore, fast input transitions, proper transistor sizing, and optimized gate design are essential to minimize short-circuit power and improve the speed, energy efficiency, and thermal performance of the chips. Static power dissipation is the power consumed by a CMOS inverter even when it is in a steady logic state and no switching activity is taking place. Ideally, one transistor is on while the other is completely off, resulting in virtually zero current flow between VDD and VSS. However, in practical CMOS devices, a small leakage current continues to flow through the off transistor due to several leakage mechanisms. The major contributors include subthreshold leakage, gate oxide tunneling leakage, and reverse biased source and drain junction leakage. As technology continues to scale, thinner gate oxides, shorter channel lengths, and lower threshold voltages significantly increase these leakage currents. Although the leakage current of a single transistor is very small, the combined leakage from billions of transistors on a chip results in considerable static power consumption. This continuous power dissipation reduces battery life, increases standby power, raises chip temperature, and accelerates long-term reliability degradation. Therefore, minimizing leakage power has become a major design objective in advanced low-power and battery-operated semiconductor devices. Before a CMOS logic gate can be used in digital design, its timing and power characteristics must be accurately characterized and stored in a standard cell library. The simplest representation is the linear delay model, where the total gate delay is expressed as the sum of the intrinsic delay and the delay caused by the output capacitive load. The intrinsic delay represents the gate's internal transistor switching time without any external loading. The second term depends on the gate drive strength and the load capacitance connected to the output. This approximation provides a fast and simple delay estimation and is useful during early design analysis and technology comparison. However, actual CMOS gate behavior is highly nonlinear, with delay and power also depending on input transition time, supply voltage, process variations, and temperature. Therefore, modern VLSI design flows replace this linear approximation with nonlinear characterized library models for accurate timing and power verification. Once a CMOS logic gate has been characterized, its timing and power information is stored in a standard cell library for use by synthesis and timing analysis tools. The table shown here represents a typical linear characterization model, where the cell delay is approximated as the sum of the intrinsic gate delay and the delay contributed by the output capacitive load. The intrinsic delay is determined by the transistor structure and internal parasitic capacitances, while the load-dependent term reflects the gate drive capability. Typical library data also includes input capacitance, output drive resistance, leakage power, dynamic power, rise and fall delays, transition times, operating voltage, process corner, and temperature conditions. These parameters enable rapid timing estimation and early design optimization with minimal computational effort. However, because actual CMOS behavior is nonlinear with respect to input slow, output load, supply voltage, and operating conditions, the linear model serves only as a first-order approximation. For accurate timing and power verification in today's nanometer technologies, modern ASIC design flows employ nonlinear characterized library models, which are introduced in the next slide. Modern CMOS logic gates no longer exhibit linear timing and power behavior, especially in deep submicron technologies. To capture these nonlinear characteristics, standard cell libraries use the table lookup model, or TLM, where delay and power are stored as two-dimensional tables instead of a single equation. As shown, short-circuit power and switching power are characterized for different combinations of input transition time, or SLO, and output load capacitance. Leakage power is also characterized under different operating temperatures, since it increases significantly with temperature. This lookup-based representation provides substantially higher accuracy than the linear model while maintaining fast computation for large-scale chip verification. Consequently, the table lookup model became the foundation of industrial NLDM library characterization and remains widely used in ASIC and SoC design flows. The power consumed by a VLSI chip is the combined contribution of several physical and electrical elements. At the device level, every MOSFET contributes through dynamic switching, short-circuit conduction, and leakage currents. The power dissipated by FET, logic gates, leakage paths, along with the other elements contribute to the chip total power dissipation. Interconnects form the communication and power delivery backbone of a VLSI chip, carrying logic signals, clock signals, and power across the entire design. As technology scales, the total interconnect length and routing density increase significantly, making the interconnect network a major contributor to chip power. The associated parasitic resistance, capacitance, and inductance increase dynamic switching power, IR loss, signal delay, cross-talk noise, and self-heating. Consequently, interconnect power has become comparable to, and in many advanced technologies even exceeds, the power dissipated by the logic gates themselves. Beyond the core logic, several other chip elements contribute significantly to total power dissipation. Large macros such as memories, PLLs, DSPs, and analog IP blocks consume substantial dynamic and leakage power. I/O cells driving off-chip loads require higher currents, while package interconnects, bonding wires, solder bumps, and PCB traces introduce additional resistive and inductive losses. The combined power dissipated by these elements increases the junction and package temperature, directly affecting chip performance, power integrity, reliability, and operating lifetime. The parasitic elements inherently created during semiconductor fabrication and physical layout influence several critical performance parameters of a VLSI chip. Parasitic resistance, capacitance, and inductance increase signal propagation delay, reduce operating speed, and degrade timing margins by increasing signal rise and fall times. The charging and discharging of parasitic capacitances increase dynamic power consumption, while resistive losses contribute to IR drop and self-heating. Parasitic inductance introduces supply noise, ground bounce, ringing, and clock jitter, degrading signal integrity. As technology continues to scale, controlling these parasitic effects has become essential for achieving high performance, low power consumption, and reliable chip operation. In addition to electrical performance, several physical and economic factors determine the overall competitiveness of a VLSI product. Larger chip area increases silicon cost and reduces manufacturing yield, while higher operating temperatures degrade performance, increase cooling requirements, and accelerate device aging. Excessive power consumption further impacts battery life and packaging complexity. Together, chip area, operating temperature, manufacturing cost, and long-term reliability are key design constraints that directly influence the commercial success and market competitiveness of modern semiconductor products. Modern VLSI chip design is driven by the need to achieve high performance while minimizing power consumption and ensuring long-term reliability. Technology scaling, higher integration density, and increasing operating frequencies introduce challenges such as signal integrity degradation, power integrity issues, thermal effects, and device aging. These factors are closely interrelated and collectively determine the functionality, performance, and lifetime of the chip. Consequently, achieving efficient signal integrity, power integrity, thermal management, reliability, and product life has become one of the primary objectives of modern VLSI design, verification, and manufacturing. Thanks for your time. In this Part 1 presentation we had overview of physical layout impact on power dissipation, and performance characteristics of a modern VLSI chip. In Part 2, we will further explore signal integrity, power integrity, thermal effects, reliability, and device qualification process of the chip. Bye for now, and hope to meet you in Part 2.